last seminar of the month. We have by Adrian Lam, his Chinese name is on the screen. And Adrian has been here for 6 months. He's still here until middle of July. And he's working on parabolic equation. His talk is on the screen. The stage is yours.
Okay. Thank you very much. It's my great pleasure to give a seminar talk at the lab. I've been enjoying my visit here and talking to different people, and it's a really nice and stimulating time for me. Today I will talk about joint work with Xiaoyu in China Normal University. The model I'm interested in is the Fisher-KPP equation. This equation is motivated by population genetics in the spreading of an advantageous allele. And later on, it is applied to study the range expansion of various animals and matched to data. Written in a more general form, if you have a nonlinearity connecting unstable to a stable state, then this kind of model is used to model other physical phenomena. The concept I'm interested in, the object is spreading speed. It is introduced by Weinberger. The definition is the following. We say the population with density UTX, okay, has a spreading speed C star, which is a positive number. If an observer moving faster than C star sees the population density goes down to 0. And if an observer moves slower than the spreading speed C star, then one observes a positive lower bound for the population density. For the Fisher-KPP equation, if the R of xt, if the carrying capacity is 1, then this simulation illustrates what's usually happen. If you have a completely supported initial data, the population grows up to the carrying capacity 1 and then expand the range in space, okay? And if you look at the temperature graph, then the expansion is linear in time, okay, with a certain speed. Another way to characterize the spreading speed is if you look at the furthest point, you pick a small constant rho, and you look at the furthest point of the level setting u of equal to rho, then the spreading speed is C star, can be equivalently given by this relation. Okay, if you divide the position of this level set by t, then the limit approaches C star. Okay, I'll first pose the question we're considering. The Fisher-KPP equation, this is a diffusion. Okay, we scale the diffusion to 1. And the nonlinear term is a logistic nonlinear term. The growth rate when u is rare is given by R of xt. This serves the purpose of the carrying capacity. And then when population grows, the growth rate decreases linearly in U. Okay, we're going to make assumption on this R of xt. Our main assumption is the following: R of xt, if you divide by epsilon, okay, if you change the variable in this way, assuming this R of xt converges to a limit, okay, then this limit necessarily have to be homogeneous in x and t. Okay, we write in this form. The question is, does the population emit a spreading speed C star? And if it does, can we explicitly determine it? A particular case of this question is the cost-shifting environment. This is a case when the carrying capacity R is a function of the moving coordinate x minus c1t for given c1. Okay. In the case when G is monotone or when G has a limit at positive minus infinity, then one can see that this limit goes to a step function. Okay, when x over t is less than c1, bigger than c1, it goes to either g plus or minus infinity. Okay, the shifting habitats question is motivated by global climate change. Okay, where the favorable habitat for growth for many species are shifting polewards. Okay, concrete examples are the boundary between forest and forest. Okay, before we go further, I'll just quickly review classical results. Okay, in the case when R is a constant, positive constant naught, then the classical result is that C star is 2 square root R naught. Okay, this is the case when diffusion is 1. In this case, the result can be proved by constructing super and subsolution. One observed that this exponential expression is a super, and for small eta, okay, this exponential expression multiplied by sine positive part of sign is a subsolution. We can imagine if you have initial data, it is bounded in between a super and a subsolution. Okay, if you optimize C in the super, you get 2 square root r. Okay, I would like to point out that the spreading speed here concerns compactly supported initial data. But for the homogeneous case, if you relax the initial data to consider exponential decaying initial data, then it depends on mu. Okay, when mu is large, the speed is the same as the compact supported data. When mu is small, then there's enhancement according to this formula. Okay, in the case when the carrying capacity is a function of x and is periodic in x, there are several approaches, okay, large deviation, recursion, and supersubstitution. Large deviation approach, one can take this transformation, okay, look at large time, large space, and look at the rate function, taking log. Okay, and the question can be rephrased into determining whether the limit of W is close to 0 or bigger than 0. Okay, that corresponds to whether the population is close to 1 or close to 0. Okay. The second approach is the recursion due to Weinberger. The idea is to turn this into a discrete problem. You first start with a Heaviside-like initial data, okay, representative of the compactly supported initial data from the right, and then you take the semi-flow. One expects this Heaviside to become a wave-like and move slightly to the right, okay, and then for any given C, you can do a translation C. Okay, so you compose this map. Okay, for different choice of C, there is actually a dichotomy. Okay, whether the whole population becomes 1 or you reach wave profiles. So by fine-tuning this C1, one can decide where the existence of C star. Okay. The last one, a supersub method. We've seen it in the homogeneous case, and actually in the periodic case, exponential is no longer a super, but it will be if you correct it by a multiplicative factor, which is the eigenfunction encoding the information in the profile of R of x. Okay. Very recently, Bersky and Adan has further developed the Hamilton-Jacobi approach. One can use homogenization arguments based on the eigenvalue in unbounded domain. They can treat recurrent, almost periodic, more general coefficient. In terms of the information in the environment, that is recurring, okay, in all the direction. If you go to infinity, then this is a fairly general result. And a complementary problem is the problem we're considering. Our problem is there is heterogeneity at the level of when x has a constant speed go to infinity. For instance, in the special case in the shifting environments, if traveling x is faster than C1t, you always see a constant environment. Slower than C1t, you see another constant environment. The question is how to consider this particular kind of heterogeneity. Or more general. Okay, in this case, the first result in unbounded domain seems to be this paper by Lee, Bilwick, Shen, and Fagan. They considered a case when G is monotone and connecting a negative habitats and expanding negative habitats and a shrinking positive habitat. Okay, and their result can be simply stated as follows. Depending on the shifting speed C1. Okay, if C1, the population persists if and only if C1 is less than 2 square root R2. Okay, and if I may, the 2 square root R2 is the predicted speed at the good patch. Okay, if it is a constant environment of here, then that's the constant speed. And this result you can actually use the supersub to show it, to see how it works. The next case we're considering here is the case when G is increasing, but it is the left and right hand limit are both positive. Okay, it is indicated in this picture. There's still a shrinking good habitats connecting with expanding less optimal habitats. Okay, C1 is a given speed, and then can we decide on this C star? Okay, here persistence is not a question because there's an infimum, positive infimum for the carrying capacity, so it always persists. Okay, so the thought experiment is the following. Okay, if C1, if the shifting speed is very, very fast, okay, very, very fast, then essentially we don't expect any effects on this from this habitat on the population. We expect C star to be equal to the speed determined by this poorer habitat. The poor habitat has this growth rate. Okay, so D is equal to 1 in everything. Okay, and in the other extreme case, when C1 is small, even 0, okay, just take it to be 0, then the population can just move here by diffusion, okay, and then we expect the propagation speed to be the one predicted by the better habitat. Now, if you look at C1, for different C1, you have a different environment, okay? And there is order relationship between different C, okay? One can easily show if C star exists, then it is a decreasing function of C1. It has to be in a way of connecting these two.
F1 is negative in that case, or positive.
Where?
F1 is negative.
Oh yeah, both are positive. Yes, yes. Both R1 and R2 are positive, and then R1 is less than R2. Thanks. In this special case, the spreading speed has this formula. Okay, I try to write it in the form of the Uchiyama results. Okay, it turns out that in an intermediate regime, the speed is determined by supercritical speed. Okay, where the exponent lambda star is given by this expression. If you look at this picture, in the intermediate regime, this C star affects the choice of the selection of this C1 affects the selection of C star. Here are the three cases. Okay, spreading at the first and third cases, the population spread at the local determined speed, and then the middle, the population spread at the supercritical speed. Okay. Third and third cases can be found in this paper. Okay, we'll just consider the intermediate case. Here, the speed written in this form, it is chosen by the apparent exponent. Okay, the initial data is still completely supported, but apparently it resembles the spreading result in this homogeneous problem, but with an exponential decaying in the data. One can look at it from a super subsolution point of view. Okay, one can construct weak super using different exponentials. Okay, and subsolution, if you do it carefully. Okay, I just want to point out. Okay, there are many choices of super that works, but the one that is given here is the optimal choice. Okay, and it gives us a C star. It will be related to the Hamilton-Jacobi approach that we'll discuss later. By looking at this super subsolution, one can obtain an estimate of the population decay along the rate. Okay, if you take x equal to C1t, you look at the super and subsolution, you can have you can observe that along this line you have a certain exponential decay in t, which can be written in this coordinate. This is the choice of lambda star that gives the ultimate spreading speed. Okay, actually this is the proof for the special case. You obtain an estimate of lambda here, and then you just look at the homogeneous KPP equation in a sectorial region, and then everything is standard. Okay, apparently what happens in the thin tail ahead of the population plays a big role in this kind of phenomenon. Okay. Actually, this motivates a second approach, a tool to look at if you want to study the tail of expanding population, a good tool is the Jacobi approach. Okay, it involves a transformation of in this form. Okay, first you take a large space, large time transformation. If you study the particular case of a traveling wave, okay, what it does is we scale the traveling wave, it becomes a sharp front. Okay, and then once you take log, you obtain this piecewise affine function. Okay, this is the object studied in the Hamilton-Jacobi equation, and we try to relate it to the phenomenon at the reaction diffusion level. Okay, for this approach, the original question was to look at the spreading, right? At which speed can we differentiate population equal to 0 or population bounded? We want to find this line. Okay, at the level of the rate function, we're looking for the free boundary between 0 and positive rate function. Okay. We apply the Hamilton-Jacobi approach. Okay. First, after the transformation, you pick up epsilon vectors in the equation. Okay, and you take log. Okay, and then you obtain this equation. Okay, this is a vanishing viscosity situation. Okay, Jacobi equation. I mean, if the limit W is positive, okay, then this term goes to 0, and you obtain a Hamelin-Jacobi equation from this part. Okay, and if W is 0, then it satisfies the equation trivial. This is the expected Hamelin-Jacobi equation. Okay, but and that is understood in the viscosity sense. And this capital R in the shifting habitat case is a step function. Okay, there's a definition of viscosity I just mentioned here. Okay, so it is a substance if you compare with a test function, and then you require at the local maximum, you replace the derivative by the test function, and then you expect inequality to hold. Okay, in the case when H is discontinuous, the classical definition for the subsolution concept involves the semi-continuous envelopes of H. Okay, to apply this approach, we need to show uniqueness. Okay, and we want to find ways to compute the uniqueness. Okay, I'll first discuss the second point, and then I'll go to the first point. Okay, discontinuous Hamiltonian generally can lead to non-uniqueness. Suppose you have uniqueness. How can you compute this? You can use the control theory point of view. Okay, you can try to write this in terms of a variational problem. Okay. This is actually giving intuition to what's happened with the selection of speed. Okay, if you have a homogeneous term here, this is a constant. Then you are minimizing the square of the path, of speed of the path, and you always obtain a constant speed. Okay, so these are the green arrow is the constant speed. Okay. In case of the shifting habitats here, okay, there is a higher growth rate when X is large, when X is greater than C1t. There's a lower growth rate when X is less than C1t. If you translate to this minimization problem, then you have smaller resistance here, and then you have higher resistance here. Okay, so actually the minimization is a compromise between these two kind of paths. Okay, one path is you go constant speed, you stay in the high resistance, and the other path is you travel faster, okay, in the less resistance path, and then you go down. Indeed, in this case, one can compute, and then we have C star is the locally predicted speed, and then in this speed, this is how the C1 interacts with this point. Okay. The second method to compute it is based on this observation. Okay. For a spreading problem, we always look at this rate function. Okay. You see the epsilon here, and the x over epsilon, t over epsilon here. In this case, you can show that W is one homogeneous in the both variable, and you can pull out t. Okay. In other words, you can always write W as in this form. Okay, so instead of looking at the equation of W, you can look at the equation for rho, which is a single variable function and satisfy this Hamelin-Jacobi equation. It is no longer initial value problem, it's a boundary value problem. Okay, if you look at this expression, whenever rho is positive, this is the constant. Okay, formally you can say that well differentiates, and this has to be 0 all the time. Rho is either a linear, affine function, or heat kernel like expression. Okay, you have two choices. You just have to figure out these constants, and you can just play around and then write down the expression and then just prove it is a viscosity. If it is, and if you have uniqueness, then you have found your okay. Determine rho, and then with rho you determine W. Okay, this is then okay. You can determine the C star in different cases. Okay, here's the summary. Okay, you take us to this shifting habitat problem. The rate function is of this form. If you can show uniqueness to this problem, then the spreading speed is determined by the free boundary. Okay, this rho starts with 0 and then grows superlinearly. Okay, the free boundary deciding where rho is 0 and rho is positive is the spreading speed. Determine the spreading speed C star. Okay. In fact, if you consider not only the shifting habitat, if your R of xt, okay, the limit exists in the following sets. Okay, you take the lim sup, you take the half relaxed limit. Well, this limit exists. Capital small r is bounded. Okay, the real requirement is that the other half relaxed limits has the same limits almost everywhere. Okay, in this case, one can derive the Hamelin-Jacobi equation in terms of this. We can show that under the assumption of this capital R. Here, our assumption is that this capital R, either it is continuous at a point or the value of R is sandwiched between the left and right hand limits. Okay, under this kind of monotonicity assumption, okay, then one can have a uniqueness for star. And of course, once you have uniqueness for star, then you have a spread. Immediate corollary, take your capital R to be a constant. Okay, the theorem becomes the following: the lim sup is a constant or not. The lim inf is almost everywhere constant or not. Then it is the C star is as predicted. Okay, that's the original formula. Here, this everywhere cannot be relaxed to almost everywhere, because if you have a moving bump, then it may enhance speed. Okay, even if the bump is small and bounded in the size, this is related to the formation of Locke's wave. On the other hand, if both statement is everywhere, okay, then this result is contained in these two papers. This is related to what's this? If the non-heterogeneity is localized, then you have C star is 2 square root. And this is the case when you have one shift. Okay, you have this in the formula. Okay, and this is the formula for two shifts. And you see, if you look at this formula, okay, it is better to state the theorem in terms of the free bounding. Okay. Another aim of our project here was to look at a slightly more general problem. It is related to the Delphi model. It's a certain kind of insects that lays eggs, and it takes a certain time for the eggs to become mature to add to the population. There's a delay in time in terms of birth. Okay, one can derive the Hamilton-Jacobi equation. That was mostly we were curious about. The corresponding Hamilton-Jacobi equation is the following. Okay, if capital R2 is 0, then you obtain the previous case, the Fisher KPP case. Okay. Here, the time delay translates to this kind of expression. Okay, but still, the Hamiltonian is increasing in the time derivative and convex in the space derivative. One can prove uniqueness for this kind of problem, provided under this condition with R2 and then both monotone, or R1 is continuous or R2 is piecewise constant. Okay, I'll briefly comment on the uniqueness of the Jacobi equation. I'll take this example. There are two main difficulties. The first one is the discontinuous coefficients. Okay, and the second one is the initial data. It is discontinuous and infinite at points. Okay, actually, this framework is carried out especially for Fisher KPP equation in Evans Uganidi. Okay, if R is continuous, then they treated initial data by using the representation formula I showed before. Here, we're going to leverage this observation that you can write it in one variable, and then we'll give a proof. It's a elementary PDE arguments. The proof is contained in these two works. First, if you have Lipschitz initial data, if you have continuous initial data, one can use the direct proof, doubling the variable arguments. Okay, and provided the discontinuity here is nice in terms of our assumption, there are jump discontinuities and monotone, then one can use the idea of Tuchheim to push the contradiction point away from the hypothesis. One can obtain a contradiction in the usual. Now, the same proof works if the super is infinite, but the subsolution is finite, because you can make sure the contradiction is obtained in the positive plane. Okay, now the final thing is that if you reduce to a one variable situation, okay, now we reduce to the first star, equation star, then to compare between two super and sub, assuming both are increasing superlinearly, you can actually modify the subsolution in this way. Okay, you pick a particular point where it's differentiable, and then extend it by the tangent. Once you do this, you fall back into this case, and then you just let this point to infinity. Since our work, we learned about more related results. Okay, our problem doesn't cover. Our problem covers the case when G is monotone. Okay, it covers the case when G is like this. Because a negative bump doesn't hurt, but it doesn't cover the case when when G is like this. You have a maximum that is exceeds the left and right side. Actually, the third case, I'm talking with Gregoire and Rashi, and it is related to a new kind of one need an extra condition in the Hammond-Jacobi equation to guarantee uniqueness, and it is the junction condition. We're still yeah. For the last part of my talk, I will talk about related problem in competition system. Okay, I just talk about them without proof. Okay, so in the competition system, one can consider it is a problem proposed by Shigesa and Kawasaki. They propose to study the spreading of two competing species with compactly supported initial data. Okay, the motivation is actually from the migration of plants in the North American continent. At the end of Ice Age, suddenly the North American continent becomes habitable to many plants. The fossil record, the invasion northward of different plant species at around the same time frame. Okay, the mathematical question is if both U0 and V0 are compactly supported, okay, for this diffusive log curve Volterra equation, how can we determine their spreading speed? Okay. Now, one expects like this happen. Faster species, okay, spread as a KPP wave, and the second species, you observe a transition between the fronts. Okay, if there's a particular strong competition assumption. Okay, and the relation to our shifting habitat is that, well, there's no shifts here. Okay, but if you know what's happening for the faster species, formally, if you say like just substitute V to be the indicator function, then at the point of view of the first species, then it is a shifting habitat. Okay, because the other species acts as an environment, a shifting environment to a particular species. One expect like this happen, and actually this has been conjectured even in a very long time. Stage invasion. There are different works here, and the highlighted ones are related to the non-local speed selection we discussed before. There's just one more mechanism. For competition system, there's pushed wave instead of, there has to be a correction to the formula. Otherwise, you see the formula we've seen before. This is lambda star, and this is the local environment. Okay, this is actually in collaboration with graduated in this lab. Liu Jihadan. At that time, we didn't have, I have had a long time to think about this since then. At that time, we constructed a super subsolution using the property that the competition model has monotone structure. You can construct super subsolution for the system to show this kind of values. Okay, one can consider exponential initial data and study the dependence on the speed on the exponential exponent. Okay. Motivated, most of these results are Cauchy problem. Motivated by the Cauchy problem, and particularly the way to construct super subsolution, we study the entire others of the PDE that exists for all time. Okay. In this case, X and T both exist on the real line. Okay. So previously, most work in the entire concern a single equation. Okay. And for the system, it's usually done in case of the bistable system when you have transition between different stable equilibrium. So here we try to look at the entire for the monostable case, and we find 5 families of the, in terms of the waves diverge. This is related to the Cauchy problem if you look at the T positive behavior. Okay, and then Salico observed that one can, for the Cauchy problem, you have supersub that works for time, large and positive time. Okay, and actually the same set of super subsolution, if you look at the different set of parameter, they works for negative and large time. Okay, you can use them to construct a merging wave, entire that is a merging wave from negative time. Okay, now before I end, there's if one really likes super sub. Okay, one can argue that, well, why go through the trouble with the Hammond-Jacobi results? Because if you work on it hard enough and then you try, and then you can show everything in super subsolution. Okay, but recently we consider a free species competition model. This is not monotone at all. Okay, and in regime we can show the spreading speed in the special case. Roughly speaking, when the slowest species, the first two species is the same as before, because before the third species comes in, you have essentially a two-species system. The real question is in the slowest species. Okay, roughly speaking, we can determine the speed as long as the slowest species, the speed is locally determined. Okay. Once it is pulled, then we can have a way to show determine the spreading pattern. And okay, with that, I want to thank you for your attention.
Thank you. Okay, next questions.
You can always make the transform to have the Hamilton-Jacobi equation, or
So, you mean here?
At the beginning, you mentioned you have W epsilon in log like that. And you can do that all the time, or you need some condition to transform into the Hamilton.
Usually, if the equation, if it's linear, okay, if the equation is linear, you always derive that, okay. And then in the case of KPP equation, the PDE is sublinear. It is a linear equation minus u squared. Okay, in that case, you can usually do that. Indeed, in the more complicated model, there is a non-local time delay thing. We only need a linear assumption on the nonlinearity to relate it to the Hamilton-Jacobi equation, because I think the Hamilton-Jacobi equation is studying the small tail of the population, right? It is related to the linearization at the trivial. Yeah.
And did you consider multidimensional problem?
Yes.
System where you have R1 at infinity and R2 at infinity. So for the multi-D, it will be.
Yes, not in our paper, okay, but I want to claim that all the formulas are the same by adding a S value around X. There is that in the limits, when we take the 1 over X over epsilon T over epsilon, then in that limit, there's no curvature effects anymore. The circle becomes too large. Yeah. The formula, the tail, and the expansion but okay, but this is what I expect, but I don't have the fear.
And the problem that you don't have minus infinity in that case of the fact that you are in a compact domain on the back.
Yes. Then it is equal to 0 at one point. Is that what you? Yeah, that's a good question. If it is equal to 0 at one point, then we may need to interpret the Hamilton-Jacobi equation in terms of control theory or things like that to give meaning to it. Initial data is infinite, right? But I think if you transform it to rho, you can still consider rho equal to 0, rho 0 equal to 0, and then superlinear. Yeah. In the radial.
Okay, I have questions online, by the way, first. In this point of view, it's exceptional that the speed of propagation is 0, and then that we can have a cooperation between species, or at least cohabit, that they can survive together. In these things are always separated.
Yes.
And when I look in a forest, it's not true. You have many. It seems that nature didn't do that.
Yes. Here we study a special case of free species. Okay, so we want to see wave succession.
Yeah.
We enforce there's a hierarchy in the species. Okay, 1 is bigger than 2, 2 is bigger than 3.
This is encoded in the coefficient you put as one.
Exactly. When they are cooperating, usually if 2 species are cooperating, they spread as the same species.
Okay.
And then their rate function is the same. Okay, they have the same tail, exponential tail, but in different ratios. You can usually consider them as one species in the Hamilton-Jacobi.
If they have different speeds, if they were at what speed will they cooperate together?
Yes, if they cooperate at the linear level, okay, if you have 2 cooperating species like ut equal to lu minus u plus v, and then dt equal to lv minus v plus u, then you cannot have one species exist without the other one appearing. Okay. If you consider their rate function, it is one Hamilton-Jacobi equation. What? It's the same. Yeah, it's the same. If you this kind of cooperative system is studied in a paper by Evans, maybe Bach, Evans, Remedies. The Hamiltonian is related to linear operator, the cooperative operator.
You present this function G with the string so far, and you can imagine that also in the bistable case, you may have similar. You can hook up reactions and that. And I'm just curious to know if there are works also in that direction, in the same line.
Yeah, this I don't know. I'm not aware of a bistable model with shifting habitats, but I would want to say that bistable waves are usually a local phenomenon. Either the wave goes at the same speed as the shifting environment, or if they are separate, then they don't interact. So that's what I would want to say, but again, no proof.
Any other questions? Okay, we stop now. So thank you again.